Alright, today I'm going to take a couple of minutes and talk you through a couple of problems dealing with impulse and momentum. Alright, so we're going to go ahead and start with this problem right here. We've got a baseball that's traveling 40.2 meters per second. That's pretty close to 90 miles an hour when it's hit by a bat. It rebounds with a speed of 45.6 meters per second. The ball is in contact with the bat for 1.10 meters a second, so what is the average force exerted on the ball by the bat? So, let's start off with the fact that we know that the baseball is traveling this way, right? There's my baseball, it's traveling that way, gets hit by the bat, and then it travels off in the opposite direction, we're assuming. Okay, so since my velocity initially is 40.2 meters per second, that means that this 45.6, which is traveling in the opposite direction, is going to be a negative velocity. Okay, and so we're going to make the assumption that the ball goes straight in and it comes straight off, which close to the bat is a fairly good assumption. Okay, now at this point we're going to say, okay, we know that the velocity is changing, therefore the momentum is changing. And if the momentum is changing, then there is an impulse. We talked about in class that the impulse is equal, we talked about it in two ways. We said the impulse is equal to the force times the change in time. And we also said that impulse is equal to the change in the momentum. So we're going to take both of these ideas and put them together right now. And so we're going to say that the force times the change in time is going to be equal to the change in momentum, which is the final mass times the final velocity minus the initial mass times the initial velocity. Okay, and so most of this information we actually have. We're looking for the force. The change in time is 1.10 milliseconds, which is going to be 0.0011 seconds. I want to make sure it's in seconds because we are in SI. The mass is 149 grams, or 0.149 kilograms. The final velocity there was negative 45.6, and then we'll go minus the mass, which was again 0.149, times the original velocity, which was 40.2. And so you can see that we have all the information that we need except for the force. So I'm going to bring up my calculator here. We're going to do the stuff on the right side first. So 0.149 times negative 45.6 minus 0.149 times 40.2. Okay, and we'll push enter. And so that's what's going to be on this side. So we'll have the force times 0.0011 is equal to negative 12.78. And then, of course, we have to divide by the 0.0011, which is going to give us a force of negative 11622. And since we did everything in SI units, that is a force of newtons. So our answer is negative 11,622 newtons. Now what does the negative mean? All the negative means is that the force was in the negative direction. Since we had a positive velocity being turned into a negative velocity, that means the force had to be in the negative direction to cause the momentum to change from a positive direction into a negative direction. And there's your answer. Okay, let's go on to another one. Let's do one dealing with just a change in momentum. So this one is dealing with a swimmer standing on a raft. So here's my raft, just one of those floating rafts out in the middle of the water. You can put the different logs and you can lash them together if you want. But yeah, there's a raft. The swimmer is standing on the raft. Okay, so this is my initial condition. The swimmer is standing on the raft. And so my system is going to be the swimmer and the raft. So I've got the mass of the swimmer times the velocity of the swimmer plus the mass of the raft times the velocity of the raft. Okay, that's my starting conditions. And then I'm going to have my final conditions over here, okay, in which I'll have again the mass of the swimmer final times the velocity of the swimmer final plus the mass of the raft final times the velocity of the raft final. Right? Since there's no other forces there that are unbalanced, that means that my system, the only thing that I'm going to worry about is the conservation of momentum within the system. So I've got the mass of the swimmer, which is 55, times the initial velocity of the swimmer, which at rest is 0. The mass of the raft is 210. The velocity of the raft, of course, is also 0. And then this is going to be equal to the mass of the swimmer final, which is still going to be 55. His mass isn't changing just because he's running. He's going to run horizontally with a velocity of 4.6. So he's going to run with a velocity of 4.6. We've got the raft, which is going to be 210, and then the velocity of the raft, which is what we're looking for. And so it should be fairly obvious that this is all going to be 0 since you're multiplying by zeros and adding zeros. So we're going to end up with 0 equals 55 times 4.6 plus 210 velocity of the raft final. So we subtract the 55 times 4.6, divide by the 210, and so you should be fairly confident with being able to do this. We'll go 55 times 4.6, right? So that's 253, which then we're going to subtract to the other side. So we'll have negative 253 divided by the 210, which is going to give us a velocity of negative 1.20. So the velocity of the raft final is going to be approximately equal to 1.20 meters per second, which makes sense that it should be about a quarter of the swimmer, right? Because the quarter's mass is about a quarter of the mass of the raft, and so the velocity should be approximately a quarter, and a quarter of 4.6 is somewhere near this. So it's a good estimate, and this is our correct answer, 1.2. Alright, so we're going to go on and we're going to try one more. We have just a minute, so we're going to go with one more with two box cars. They're being assembled in the yard. You've got two that are cart 1 and cart 2, right? And it says that cart 1 is moving along with a certain mass, and that car 2 is coming up behind it, right? It says that car 2 is approaching car 1 because it's going faster, and it's going to approach, and they're going to link it together. Alright, and so this is my initial conditions over here. And then my final conditions, I'm going to have car 1 and car 2, which are now linked together. And if they're linked together, that means that their velocities are going to have to be the same. So the velocity of 1 final is going to be equal to the velocity of 2 final. Okay, so let's go ahead and write our conservation of momentum problem here. Okay, so we'll have the mass of car 1 times the velocity of car 1 plus the mass of car 2 times the velocity of car 2, which is then going to be equal to the mass of 1 final times the velocity of 1 final plus the mass of 2 final times the velocity of 2 final, right? Now we're given most of this information. We're given the masses of car 1, so 65,000 times the initial velocity, which is 0.8, and then we've also got car 2, which is 92,000 times 1.3. And now when they meet up, their mass is still going to be the same, 65,000, but we already said that the velocity of car 1 in the end is equal to the velocity of car 2 in the end. And since those two are equal, we can represent them with the same variable. Okay, if you want to use a v1f for both of them, you can. I'm just going to put in an x because I know that those are both going to be the same thing. And so I'm looking for x is what I'm going to be solving for. The mass of 2 is 92,000. And then again, it'll be times x because velocity of 2 final has to be the same as 1 because they're going to be rolling along together. And from this point, it should be fairly obvious. We're going to add these two together, right? So we'll add the 65,000 to the 92,000, which is going to give us 157,000. So 157,000 x, right? Because 65,000 x's plus 92,000 x's will give us 157,000. And then on this side, we'll go ahead and multiply and add. Okay, so we'll move this over. We'll go 65,000 times 0.8 plus 92,000 times 1.3, which is then going to give us 171,600, which will be on the left side. We'll then divide by this 157. So divide by the 157,000, and we get our answer, which is 1.09. So 1.09 meters per second will be our x, which is the velocity for both of the cars. Okay, and that's all there is to it. There's 3 examples. One was specifically an impulse, and the other 2 were conservation of momentum. Hopefully that was helpful, and you'll now be able to complete your homework. Good luck.